So, dear colleagues, I'd like to introduce you our speaker, Dr. Al Kenany from the California Berkeley University. He is a PhD of the Professor Carl van Bibber, who was talking about the axions the 6th of September. So this talk is devoted to the metamaterials for the tunable plasmonic resonators. So please, Carl, you can start.
Okay, thank you very much for giving me the opportunity to present some of my research here at the Department of Nuclear Engineering in Berkeley. And I understand that Professor Carl van Bibber, he already presented a few weeks ago and talked about the axionic dark matter research. Today, I talk about metamaterial research for the Tunable Plasmonic Resonator. And maybe some of this stuff is repeating because Professor Carl van Bibber presented some issues about the cosmological background of the research, but I would like to summarize this in the beginning in my talk. So I would talk about the search for dark matter axions and in general about dark matter and what kind of efforts the various institutions putting in this field of research. And I will talk about the tunable plasmonic holoscope and wire arrays metamaterial, then discuss some of the experimental results and the concept for practical tunable array. Let us start with this, why we are doing this research. So it's very important to understand where we are in this field. We think that as the universe was expanding, there was a dark energy that accelerated the universe, and baryonic matter was created. And there is a part of the matter that was created is dark matter. The dark matter was postulated in 1933 by Fritz Zwicky. He explained that gravity induced by luminous matter alone does not account for galactic dynamic. So it means you observe the universe, you see luminous matter, and then you calculate how much mass is there, and then it does not work with the numbers, that there must be some missing mass there in the universe, much more than the visible mass. And that's what he called dark matter. And there must exist a form of matter that does not interact strongly with the standard model of particles. So it means not in the electromagnetic domain, non-observable. The only way that it interacts is through gravity. Observation showing that the galactic rotation curves, instead of expected to be in the visible disk, it's expected to be going lower with the velocity. Instead, it's actually gaining velocity, and then the observation stops from the starlight, and then later on in the 21 centimeter hydrogen observation, it shows that the speed, the velocity is actually accelerating rotational velocity, and with this there must be some additional gravitational force that causes this phenomenon. We also observed that the galactic halos, the galaxy suspended vast, essentially spherical halo of cold dark matter. And calculation of this density, showing that the density of dark matter in the solar system is also approximately 0.3 per mass per cube centimeter. So based on this cosmological introduction, we think that there is a 25% dark matter in the universe, where hydrogen and helium and baryonic matter is very, very a small percentage of the existing universe, and then 70% is dark energy, which is responsible for accelerated expansion of the universe. So now we look into what is dark matter, and then there are competing theories. I will highlight two of the projects that I personally works on, which is the one theory suggests that it is a WIMP particle, which is weakly interacting massive particle, is larger than the neutron, and it interacts only in the gravitational domain, and there is the axion. A lot of research efforts are done in very expensive type of research. There is the super CDMS experiment at Snow Lab, is in 2 kilometer underground, and the search mass criteria is 10 to 100 GeV with a cross section of 10 to the minus 40 square centimeter. And the way this works is using germanium detectors in electrical field. And when a WIMP particle interact with a germanium nuclei, it will recoil at an energy of tens of keV, producing electron and electron hole, and this can be detected by ionization electrons and phonon in the germanium crystal. There is also another WIMP method of searching, which is the xenon 1T experiment. It's a 5.9 ton of liquid xenon, and it has 494 photo multiplier tube, and it's based on scintillation effect. So when the dark matter hits xenon atom, the atom recoil and excite other, causing a flash of light. That's the first event. And then after that, the free electron will travel up applied in applied electric field. When it hits the surface in the gas, excite more xenon to make another light flash, and that's the S2 event. And then by this, we can measure the mass and the mass and the energy of the particle. Now, why we are motivated for an additional theory? It's arises from solution of the strong CP problem. The Peachy, Quinn, Weinberg, and Wilczek paper. They publish a paper that there is a strong CP problem, CP violation, and then the axion, if it exists, it will solve this problem based on the cosmological model. And the axion should have a very light mass, 10 to the minus 9, 10 to the minus 3 EV. And the axion is a pseudo-scalar light, it's a kind of light cousin of the pion. And again, the coupling are exceedingly very weak. And then the two photon coupling is designated in this symbol of gamma, axion gamma gamma, which it means 2 photon and 1 axion. Roberto Peachy and Helen Quinn proposed this in 1972. I show here the solving of the strong PC problem at the Lagrangian. And then the Steven Weinberg and Frank Wilczek proposed mechanism that lead to a new light, the boson particle, which we call it the axion. And then there is a calculation for the mass. There are very complicated calculation and cosmology with the cosmological background, where this axion field could exist, and what is the mass constraints. There is a supernova constraint, there is a horizontal branch stars constraint, and of course the expansion of the universe. And then this will put a constraint on the mass of the axion, which is very important for us to know how to where to look and how you design your detector, at what criteria you are looking, what mass and what energy. So it suggests that if we are just happening for the scanning rate, the scanning rate is extremely large. It would be much larger than and greater than the age of the universe. So if the scanning rate calculated correctly, that an axion will interact with within a photon, and it will produce another photon. So we have to look into another method effects. And here comes the Primakov effect, which suggesting that in a magnetic field, if there is a cavity, then with a high cavity with a high Q placed in a strong magnetic field, and if the frequency of the cavity is matching the mass of the axion, which is mass is a type of frequency, then a resonantly enhanced conversion to weak microwave signal occurs. And you see here the Lyman diagram that when an axion interacts with the virtual photon, which is produced by the magnetic field, then it will convert to an actual photon that is measurable. So this is most practical for microwave cavities with radius in order of centimeters, and maybe we go to meters, corresponding to frequencies to 100 megahertz to 10 gigahertz, and that would correspond to 0.4 micro EV to 40 micro EV. But the axion mass may be larger or smaller. So we have to look for some other principles that we can apply for our experiment. And the heart of the problem is that the frequency of the mode determined by the boundary condition of the conducting cavity. So we built the experiment at Berkeley, Yale, the haystack, which is the holoscope at Yale sensitive to axion called dark matter. It consists of the cavity, of course, with the strong magnetic field. And the cavity, it's tuned to a certain frequency that's match the axion proposed frequencies. And then we have the Josephson parametric amplifier. There's a mixer and then an FFT, and then this way we extract the signal. So based on tunable microwave cavity permeated by strong magnetic field. Now, please note that the radius here is proportional to the inverse of the frequency. For the experiments at Yale, we are looking into signal power of 10 to the minus 23 watt. Let's look into this carefully. What we are measuring here, are we expecting that comes out from the cavity, is determined by cosmological parameters and by experimental parameters. The cosmological parameter we cannot control. It's dictated by the physics and by theoretical our understanding of the standard model of particles and the cosmology. And then part of it, it's the mass of the axion, what we are suggesting what the mass is, then the density of the dark matter, and then the observation of star in the globular star constrain the axion photon coupling, which is this parameter here. But more importantly is the experimental parameters. What can we control in the lab? So the important part for cavity design, of course, is the cavity volume. And that's one parameter that we can control. Then the power of the signal increased by this square of the magnetic field. That's good. It means the higher we apply, when higher the magnetic field, we can improve our signal, which is actually signal to noise ratio. And then the frequency, the tuning frequency of the cavity. And then we have two important factors. One is the form factor, which is telling us how well is the magnetic field aligned with the electric field inside the cavity. And there is the quality factor of our measurement. So what we're looking at, we need a good quality factor, we need good form factor, the overlap of the axion-induced electric field with the magnetic field, and we need volume as large as the magnetic field can permit. This is also a limitation because we have to have the cavity sitting inside the bore of the magnetic field. Then it has to be tunable. We have to find ways how to tune this. And then we will go up to 100 gigahertz in frequencies and other important features, which is the freedom of the modes. TE mode, TEM mode, and the avoidance of mode localization. So at Haystack, and the actual experiment is at Yale, we have a copper-plated cavity with off-axis tuning rod. You see it here. That's to tune the frequency. We can tune from 3.6 and scan all the way to 5.8 gigahertz. This is all inserted in the dilution fridge. And we apply a field of 9.4 Tesla, 10-liter magnet. And of course, the signal is amplified using Josephson parametric amplifier. And for the tuning, we use the stepping motor for linear motion coupling and auto-cue piezoelectric device for main tuner. That's when you rotate the asymmetric rod, then we changing the frequency inside the cavity. Now here you can see that various cavities has a limitation. We were able to increase the frequency to 7.5 gigahertz as a thesis, research thesis by my colleague Maria at UC Berkeley. And now beyond that, it become really problematic because when we go higher in the frequency, the cavity become much smaller, and then it become not practical for experimental purposes. So I want just to say that the various experiment here again, just to see the ADMX, for example, the ADMX radius is 25 centimeter. They use a big bore magnets. In Haystack, we have a much smaller cavity. So this is an advantage, but we have a high magnetic field. And then how to get, the challenge is how do we higher frequencies with a practical large volume? And here comes the basic idea for dielectric with index of refraction larger than 1. But what we are looking for, we look for a material that has index of refraction less than 1 to boost the frequency, to go to higher frequencies at the same volume, and that would be plasma. However, plasma is very hot, so we keep this in mind. Let me talk a little bit here of the axion. That could, the mass axion could be anything from less than 2 to the minus 10 to the 10 to the minus 2 eV. But the cavity holoscope can only feasibly search over 1 to 50 MeV range. On the low frequency end, the cavity must fit into the magnet, and then on the higher frequency, the cavity become very small. So here comes a publication about the metamaterial surrogate for plasma. The Stockholm theory group has published a paper proposing a very simple application of metamaterial, which is a 3D array of very thin wires. And this paper is published by Lawson and Miller, with suggesting the tunable axion plasma holoscope. So what is this exactly? They suggest that in the plasma frequency in a metamaterial is complex. The analytical and simulation shows that the response of plasma loaded cavity with a certain omega here, 30 gigahertz, show us that there is the calculation of plasma E field within conducting cylinder is feasible, which is driven by the axion field for a plasma around 30 gigahertz. This will match a mass of 26.2 micro EV for the axion. The idea that when this array is built, then we can measure in the magnetic field, we can measure in the electric field, and the basic of the idea that we can, when an axion is interacting with the plasma, we can measure this inside the metamaterial. It provides no guidance on how to resonate or how to tune it. And no one, to our knowledge, has investigated the incorporation of this metamaterial in a cavity. So there are more studies on tunable plasma holoscope. The cavity and the electric holoscope use a broken translation invariant to convert massive axion to massless photons. And the wire array material exhibit plasmonic behavior and may be feasible for a resonator for a dark matter axion experiment. So here comes the most important relation in the geometry of the very thin wires. For a square lattice of wires, we have a relation that relates the electron density inside the wires and the effective mass to the geometry of the grid of the wires. So we have two dimensions that we cannot that we can control. Here is a distance between an x direction, which is later on translate to distance between frames. So if we put one array at a time in a frame, then the distance in x direction will be the distance b between the frames, and a would resemble the distance between the wires. So if we take, for example, a 50 micron OD wire and we put them at a distance of 5 millimeter, that will correspond to a plasma frequency of 10 gigahertz. So we did some research on Belov equation to Belov improve the calculation. We were working first with the Pendry equation, but we see that now there is another parameter added, which is B. We looked into the selection of material in terms of the skin depth and selected gold to be the best for our application is 0.77 micrometer. And then we looked into various radius of thin wires. And we end looking into wires that they are between 10 micron and 100 micron. And started to design a prototype that we think that if there are multiple frames with the control distance, which in this case is the parameter B, and then the control distance between the wires, this will give us a control of the frequency. So we start building a prototype for for multiple purposes. Feasibility of thin wire lithography later on. And we want to make sure that this concept work first in the lab. So we use an actual physical wire, not deposited gold deposit on substrate. And we made some calculation about the fitting of the data. So when we measure the data, we apply equations similar to high pass filter based on Drude theory of solid. So we built our first 3D wire array. It consists of 20 frames, a stack of frames made of tungsten gold-coated tungsten wires. And we apply antenna and then connect it to the VNA. And of course, it's all excluded from external microwave sources, and we put all in EcoSorb. And we fabricate wire frames with 50 micron OD and spacing of 5.3 millimeter. And then about how we control the distance here, the tunability of this system, we use spacers. We use spacers between the frames, and the number of spacers will determine how far the frames are in the three-dimensional space. And we are measuring the S21 in the Z direction. And so the measurements for wire array in various configuration with polarization in the Z direction. Here you see the fabrication stage of the wire frames, which is 10 by 10 and cut in 8 by 8 inch. And then you see here the spacers that control the distance between the frames. And then all the experiment included in the dark cube and assembled inside the EcoSorb panels. And our measurements were very successful. First, we want to see the dependency of the number of planes. So at 5 planes, we don't see a lot of filter effects on the plasma effect on the microwave propagation. But then as we increase the number, we see that at 20 frames, we get pretty steep function in the S21, which indicates that there is really a plasmonic behavior here, and that the propagating microwave is interacting with the plasma, and the entire system is act as a high-pass filter. And this is important that it means when we increase the frames, the number of frame, which increase the number of wire, which increase the density of the plasma, which is the electrons in the metal, then we can control the filter, and then we can control the frequency, where this cut frequency is exactly. And then by controlling the number of spacers, we can tune the system to a frequency between 7 and 14 gigahertz. And here you see again, where the fit, we use a fit function, least square fit, and then it's perfectly matching the data. Then we went to the tunability, and then we looked into the tunability of the system. And then as you see, when we vary the B, which is the distance in millimeter, and we keep the distance, the spacing between the wires, and we add more frame, but we control the spacing in between, we can gain various frequencies, as you see here, with a very sharp curve. It means if we have a method of mechanical tuning, we can actually tune this frequency to match the axion frequency which was the original purpose of this experiment. And then it's very important to know that the first experiments with the just varying the number of the spacing, we use a square grid. It means A equal B. But here, as we break the symmetry, we enable the explore breaking square symmetry, in which case this is matching the analytical solution of Bailoff equation, and that's where our data is exactly matching on the analytical computation of Bailoff equation. Then we explored two various ideas about variating the correlation and then the relative position of the frames compared to a reference frame. And then we vary each frame to a certain degrees. And you see when we vary to 30 degrees, 30 to 22, 15, and 8 degrees, there is a tuning happening here as well. And although the distance between the frame and the wire frames are fixed, but there is a tunability. We can tune the frequency also this way by variation of the orientation of the frames relative to each other. Then we explored another variant, which is the relative translation of intergrid. So we want to see if the intergrid is in a square order or in triangular order, it will do any tuning. I know that this is possibly in the simulation, it's possibly showing that there is a tunable max and min here, but in this case, we didn't see any change in the frequency, and probably this is because it is below the mechanical tolerancing in the system, that the variation is below the mechanical tolerancing in the system. And then I want to say here about what is important in this experiment is very preliminary. We just want to make sure that that this system work and it is tunable, and that a type of cold plasma, according to Drude theory of solid, it does work as a plasma, and that what we have to look into further is how to improve the quality factor. There is one thing here maybe important to understand, that if we increase the number of frame, which it means we are adding more and more wires, at some point when the resistivity losses dominate at low number of frames, but when we increase the numbers of the frames, we increasing the density, but we adding more and more wire material, the reflective losses dominate. It means that at some point there is a maximum for the quality factor, but it's not that when we keep adding it, we are improving the quality factor. This is something that we have to look into. And then the other thing, that the mode density, the electric magnetic field factor of TMTE and TEM mode in a cylindrical cavity, it will follow, of course, the Maxwell equations. And at this point, I haven't done any look into how the mode behaves inside this detector that we are building, that consists of the multiple frame. We have to look into that. And in terms of range of axion mass, the range of axion mass, it can, with this setting, using the wires with this setting, without looking into now electronic side, but just the plasmonic resonator itself, we can look into 100 to 300 micro EV axion mass. But at some point, if, for example, here, if we can use a 1 millimeter distance on an array that's deposited gold on substrate, and we separate them very in a 1 millimeter order, and then we using a thin frame, then we can go to a much higher frequency. But what I'm saying that there is a limitation on the matching this frequency to the search frequency that we are targeting on the axionic mass. Then there is the practical tuning and implementation in the experiment. And there are such suggestions made by Professor Carl van Weber about how to tune those arrays by using a tilt mechanism. There is also a competing ideas and approach that we can do the tuning at the FPA, at the JPA, the amplifier level, and then we can do this electronically instead of the mechanical. Here is a suggestion of the spacing between plane that could change by attaching it to a pivoting frame mechanism with an array of antennas. So the summary, what I'm talking that a two-dimensional wire in a multiple two-dimensional, which is three-dimensional actually, it is demonstrated that it confirmed the theory, it confirmed Below equation in the lab, and its preliminary offers potential solution to reach higher frequencies for axionic dark matter experiment. But there are several outstanding questions that we have to answer, which is determining the effective quality factor, especially if we want to go into low temperature or cryogenic temperature, which is obviously we're going to go to improve the signal to noise ratio when we looking in a very low signal signal power that we are measuring, and how this system, this array behave in confined conductive volume. If we install this in an antenna, if we install the entire setting in a cavity, how this going to behave. And then of course the antenna design of plasmonic resonator, as the Compton wavelength may be much shorter than the physical side of metamaterial array, and what the design and calibration system would be, and emulating an axion driven source, and then of course the mode density and the mode behavior. Future Berkeley work will include exploring plasmonic behavior on larger array fabrication, and then maybe we are looking into printed circuit or printed on thin dielectric sheets and tunable engineering prototype. Thank you very much for listening. That's a very brief presentation for the research that we are doing.
Thank you all for the very interesting talk. So dear colleagues, do you have any questions to Al? If yes, please raise your hands. Okay, so Pavel, raise your hand. Pavel, please.
Yeah, thank you. Oh, thank you for a very nice talk. Very interesting indeed. I just wonder, in the part of your experiment, when you was measuring these transmission coefficients, have you seen any trace of TEM modes in the system? Yeah, because usually if you excite these arrays differently from the sides of wire ends, we see many vibratory resonances. Have you seen something similar here, or it's just because of the polarization you do not see them? Can you comment a little bit?
So we haven't looked into that. There are some simulation works done with the Stockholm group about how this mode behave, but just looking into the experiment, I can see that the outer boundaries of this cube of a plasma, let's talk about that, or the cube of wires frame, that the outer display different behavior than the kernel inside. And then now we are looking into ways how to measure this mode. And I think that myself, I haven't looked into this, but it seemed to me that this is something that it has to be well understood.
Pavel, it's clear, right?
Thanks. Yeah.
Okay, so the next question from the Dmitry Karlovitz.
Yeah, thank you very much for the very nice talk. So I have the following question. So are there any physical constraints for the lower limit on the axion's mass? So how small the mass of the axion could be in principle, and what are the physical constraints? Thank you.
So there are cosmological limitation for the mass of the axions, and it keeps changing by theoretical physicists, especially by cosmological models. And then there is a limit of, I think that there is, it went from 6 eV, and then the latest talk by Ben Safdie, it goes up to 40 micro EV. So from 6 micro EV to jump to 40 micro EV and beyond. So it looks like by improving the cosmological model, it's rather going up, the mass going up, and than going down in the calculations. And this was just recently a talk, like just last week, by Ben Safdie. Yeah, but we were looking into 6 micro EVs, and then goes more to 40 EVs at this point.
Mm-hmm. Thank you.
Thank you. So any other questions? So actually, I have a few questions to you. So the first question is regarding to the slide 13. So how strong should be magnetic field to detect axions? So from the formula in the slide 15, it looks like that it should be as much as possible, right?
As much, yeah. So so I can. The thing here with the magnetic field, it's really, it should be as high as possible, because we look into this B square, and this is good that we do B square in the that will improve the signal. So the better, the higher the magnetic field. However, there is a limitation of how big is your magnet, and it will determine by the bore. So, you know, if the experiment has to fit into the bore. So if you make higher magnetic field, it's going to be smaller. And then if we, at some point, for example, at Yale, we use 9 Tesla magnetic field. This parameter, it can only improve the signal, but there is no limitation. The only physical limitation in the lab, that your detector or the cavity, it has to fit inside the magnet. That's the only limitation. But at this point, for the measurements at the haystack experiment, for example, it's at 9 Tesla, and then we will be we are looking into more higher magnetic fields, probably 14 Tesla or so. But this become really a custom design, and it throw the budget of building a magnet for the experiment out of proportion. But there is no required limitation, and unless you really want to improve your power signal, the measured power signal.
Oh, if we have higher magnetic field, there is a higher inhomogeneity, right? So
correct.
How it counts here in this formula, in the form factor or in the cavity volume?
So it does come into it does leak. These parameters leak into the form factor as well, because this form factor determine how well is aligned, the magnetic field is aligned with the axion, right? So if there is a higher magnetic field, then we probably have a better form factor in this point. And that will add to improving the signal to noise. But at this point, this form factor, it's really as a complicated calculation. It has one part is in the experimental, but it has also one leg in the theory, because we are talking about alignment of electric field of an axion. So that's kind of a complicated field. It's beyond my theoretical physics background, but my understanding that the magnetic field has to be aligned, and it will show up as well. So the uniformity of the magnetic field is significant, which it shows up in the form factor.
Okay, thank you. So any other questions, dear colleagues? Maybe one last from me, from the practical point of view. So are you going to make some experimental measurements at low temperature with your structures at, yeah?
Yes, it's absolutely down the path, but this is up to the Stockholm group. And of course, you know, when this become like what I showed, what my research, I show that this concept of using a plasma, which is the electrons in the very thin wires, that it can be aligned and it can be tuned, and then it has a certain quality factor, and then this kind of what at the end it will be a detector head. That's very basic design in the lab that it works. Now, if we move further, I can see that this is going to be at some point to be more controlled physical dimensions. It has to go into deposit, gold deposit on substrate, very thin wires, multiple layers, and it will be, of course, in low temperature, like cryogenic temperature, as the experiment now at Haystack. At Haystack is, I think it is at 50 millikelvin, maybe less. And so the cryogenic is part of this business. You know, the signal to noise ratio has to be improved, and you have to eliminate all other phenomena happening in this case in the metal. And so it has to be cooled down to sub Kelvin in order to make this works. And this is probably down the road, but this is up to the team and then the Stockholm University Theoretical Physics Group.
Okay, thank you. So if there is no any other questions, I'd like to thank speaker again.
Thank you.
Yeah,
My
thank you very
pleasure.
much.
Thank you.
Yeah, goodbye.